Now that we've looked at the resonance view and the molecular orbital view of conjugated dienes, we can now think about the physical consequences of those views. As we saw in the molecular orbital view of conjugated dienes, we know that there are 4 electrons in that entire pi system. So we saw that 2 of them are in the psi1 orbital and 2 of them are in the psi2 orbital. We also saw that the 2 electrons in the psi2 orbital are the HOMO electrons, right? These are the electrons involved in interacting with other substrates, namely electrophiles. So this represents the traditional view of a double bond, single bond, double bond, right? Because you have that node, the psi2 orbital has the node in between C2 and C3. We also saw that the resonance view gives the same the same picture as the most stable resonance structure. However, there still is resonance, which stabilizes the structure, and we saw that in looking at the psi1 orbital. So the psi1 orbital is lower in energy than the typical ethylene bond, and therefore that provides stability to the system. And we can see that in a couple of ways. So the first physical way that we can kind of visualize that is if we compare single bonds and double bonds to a conjugated double bond system. So I'm showing butane, 2-butene, and then 1,3-butadiene. And we can simply look at the bond lengths of that bond between C2 and C3. And for butane, that bond is 1.53 angstroms, and for 2-butene, the bond is 1.32 angstroms, which we would expect it to be shorter because it's a double bond. So, so is there some double bond characteristic in that 1,3-butadiene? Well, we see that the bond length is pretty close to a single bond, but it's still a little bit shorter. And so again, this supports that view that that this 1,3-butadiene takes on the double bond, single bond, double bond approach, but there's some resonance that's stabilizing that. Now, one of the things that we can then think about is if there is some pi character to that C2-C3 bond, then we can think about the conformations of that bond. We know that there's, typically speaking, in a single bond, there's free rotation about that bond, right? And so if I rotate that C2-C3 bond, then I get this the following structure here, right? And so the conformation on the left we call S-trans, and the conformation on the right we call S-cis, because that S simply denotes that we're rotating about a single bond. And we can look at the barrier of rotation about that bond and see if there really is a barrier. And so when we do that, we see that the rotation barrier is 19 kilocalories per mole. Now, what does that mean? So we have to put that into some type of context, right? And so we can look at, well, what's the rotation barrier about a carbon-carbon single bond? And when we do that, right, so the rotation barrier about a carbon-carbon single bond is 12 kilocalories per mole. So we see that there's a little bit higher energy for the rotation, but at room temperature, this is essentially insignificant. And so we can see that these butadiene systems, conjugated butadienes, are still going to be able to rotate from the S-trans to the S-cis. Now, having said that, S-trans is still favored by about 10 kilojoules per mole. And the reason for this is fairly simple if you take a look at the structure. So here I'm simply drawing 1,3-butadiene, and what I'm going to do is I'm going to highlight the hydrogens that are coming off of that in the S-trans conformation. So when I rotate about that bond, now the hydrogens you see are in pretty close proximity to one another, and so their electron clouds are going to be colliding with one another, and we see some steric effects. And this is why the S-cis conformation is a little less stable than the S-trans conformation. Another way of looking at the physical consequences of this conjugated system is by thinking about the heat of hydrogenation. So we know that we can measure the stability of a molecule by looking at its heat of hydrogenation, and this is something we did with alkenes, right? So if I take one butene and I hydrogenate it, I get one butane, right? And I can measure the delta H of this reaction, and I see that the delta H is minus 30.3 kilocalories per mole. Now, if I look at, in this particular case, I have 1,4-pentadiene, and I hydrogenate it, I get pentane. And we would expect, because we're simply hydrogenating two separate bonds, then we can predict what the delta H of that is based on our knowledge of the heat of hydrogenation of 1-butene. So if 30.3 kilocalories of energy is released for one double bond, then I would expect to see about double that for two double bonds, right? And when I measure that actual value, it is actually really close, so minus 60.8 kilocalories per mole. Now, we can, you should always think to yourself, well, is this arbitrary? I mean, it's simply one data point. And so we can look at a variety of dienes, and so here is 1,5-hexadiene, and again, we have two double bonds, and so we would predict the delta H for this to be 60.6, and when we measure it, the actual value is minus 60.5 kilocalories per mole. So again, you see a very close approximation. And we can average those two together, and we get minus 60.7 kilocalories per mole. So very close to what we would predict to be the heat of hydrogenation. Now notice for these two examples, both of them are non-conjugated. So let's now look at a conjugated diene. And so we can look at 1,3-butadiene. And when I hydrogenate 1,3-butadiene, again I get butane. And so again the predicted value would be minus 60.6 kilocalories per mole. So the actual heat of hydrogenation is a little bit lower than that. It's minus 57.1 kilocalories per mole. And so when we look at the difference between, that average, which we call, which is the 60.7 kilocalories per mole for the two other dienes, we see that that difference is 3.6 kilocalories, and we attribute that to resonance stabilization.